Yes, I'm Adriaan Jacobs. I'm the author of this meme. I'm also the author of this paper, which I want to present to you. So I will be talking about store-only bounce checking, and why you shouldn't do it. This is work that I did with my advisor, Stijn Volckaert, who is also a co-author. We are from the DistriNet research group in KU Leuven in Belgium, just like Victor from earlier. So I don't think I have to tell the WOOT audience that our entire digital lives are built on a foundation of security bugs. Some of them already exploited, some of them not yet exploited. And what all of these headlines have in common is that they're all memory safety issues. And so memory safety issues, these are things like dangling pointer dereferences, use after free, out of bounds read, out of bounds write, things like that. And they're particularly insidious because they don't just break the semantics of your application, but they break the semantics of your programming language, right? So they are very subversive. And that's why they're typically very severe. They lead to arbitrary code execution, remote code execution, things like that. And so out of all the high severity security bugs, the really critical security bugs, 70% tend to be memory safety issues. So we've been trying really hard to solve this problem, and the question is, why haven't we solved this problem yet? Now, of course, this is a nonsensical question, because as we all know, memory corruption is a solved problem. But bear with me, I will explain to you why it's hard anyway. So what we typically try to do, or one way to go about this, is to retrofit memory safety into memory unsafe applications, right? And so we would typically modify a compiler to instrument the program automatically with bounce checks, dangling pointer checks, pointer validity checks, stuff like that. The problem is that you have to put very frequent checks into your application. So at every memory access, you have to check the bounds of the pointer, things like that, and that leads to high overhead. Now, of course, when you have high overhead, what do? You try to design hardware acceleration, right? But that has proven to be quite a challenge. So Intel has come up with an attempt, Intel MPX. I don't know if anyone remembers that dumpster fire, but it was deprecated after a few years already. And I will show you later why. So it's been really hard to sort of generalize hardware acceleration for bounce checking without being tied to a specific bounce checking design, which then will have its own problems and cause deprecation. And then there's a bunch of compatibility issues that are a problem as well. Sorry, Alyssa, I will change the slide. So what has seen some success, though, is partial bounce checking. So applying bounce checks to only part of your program, only part of your memory accesses. And the advantage is that you get a lower performance overhead. And also the compatibility issues are smaller because you only have to sort of adapt part of your code to fit in the bounce checker. And so one approach is to bounce check some security critical part of your application. Or what you can also do is look at which bounce checks are contributing a lot to the overhead, but not a lot to the security benefit of your program, and then remove those, right? There's some existing work about that directly affects that security performance trade-off. But what I want to specifically talk about is what's called store-only bounce checking, where you remove all bounce checks on memory reads. And that might sound crazy, and it should, but historically people haven't thought it was crazy. And so I've actually thought it was a quite interesting proposition, quite an interesting idea, where they thought, okay, invalid writes are typically what you want as an attacker to achieve expressive exploitation, right? You want to override security critical data, you want to override code pointers, do control flow hijacking. That's what you want, but writes are actually only a subset of the memory accesses that an application executes at runtime, so only about 20% typically. This is the figures for Spec CPU 2017. And so if we only instrument invalid writes or memory writes, we instrument a subset of the memory access of the program, but we can cover sort of the majority of the attack surface, the majority of attacks. So it's a very interesting proposition. There have been some very, in hindsight, embarrassing claims about this approach in literature. And so let's investigate it a little bit more, right? So let's look a little bit at how bounce checkers work, right? So this slide is a little bit complicated. You only have to look at the first part for now. The basic challenge that the bounce checker has to solve is whenever I'm dereferencing a pointer, I have to figure out what object this pointer is supposed to be referring to, right? What object this pointer was originally derived from, what is the intended referent for this pointer, and then I can check whether I'm still in bounds of that intended referent, whether the intended referent is still alive, things like that, right? That's the basic challenge, and there's two main approaches to solve this, but any bound checker design, the own goal is just to answer this question. So one of the approaches is pointer-based, which means that you will explicitly track the intended referent along with the pointer throughout your program. So a typical approach is a fat pointer, right, where you will have a reference to the intended referent or some metadata about it, like the base and the bound of the intended referent, together with your pointer in a bigger pointer, which you propagate throughout the program. I think most of us are familiar with this approach. So that's one way to go about it. And then at pointer reference sites, of course, the metadata is already there. You've already loaded it together with the pointer, so very simple. In order to be pointer-based, it doesn't have to be a fat pointer. You can also store the intended referent metadata disjointly. But then, of course, you have to maintain some kind of way to look up the metadata of the pointer at the pointer dereference site, right? And so that you have to link the two. And so, for instance, softbound, which is some famous work from over a decade ago at this point, uses the address of the pointer to link it to its metadata. That's just a design decision. It's not a bad one, actually. So this is one approach. Another approach is to say, okay, why are we tracking this intended referent all over the place? That's so expensive. Let's just not lose it in the first place, right? And so the idea there is to constrain pointer arithmetic, so you never go out of bounds of your intended referent in the first place. And so you're always pointing to your intended referent. And so whenever you have a pointer reference, you can just look at the current object you're accessing and then figure out the metadata from there. So yeah, it doesn't mean that you don't have any metadata. You will still have like some bound metadata based on the object you're currently accessing. And so these typically instrument pointer arithmetic, constrain pointer arithmetic. That also leads to many of their compatibility issues. So regardless of everything I just told you, many people have been deploying these bound checkers, regardless of their pointer-based or object-based nature, in a store-only way to get those benefits I said earlier. So let's look a little bit at how that works. So this is a simple program where we load a pointer from an array of pointers, and then we dereference that pointer in a memory write. So this is how you would apply a store-only bound checker to it. Whenever you're loading the pointer from memory, you're also loading its bounds metadata. So I'm using the example of a fat pointer here, but everything I tell you holds for all bound checkers designs, which I will also show. And then when you're actually dereferencing the pointer, you will use the loaded metadata together with the pointer that you loaded, and you will check whether the pointer is valid, right? So a normal bound checker would also check the validity of this memory read out of this user ages array, but not a store-only bound checker, right? It refuses to do that because it's trying to save performance. And that's actually the core problem. So when you don't check the validity of this memory read, you're allowing an attacker to essentially load any pointer they want out of this memory read, because the attacker can take control of I and can go out of bounds here, right? And let's have a look at what is out of bounds, right? There is this very interesting pointer that points to some security critical isAdmin boolean. That the attacker can load instead, right? So instead of one of the pointers in the user ages array, the attacker can load the isAdmin pointer. And when they do that, they can override the isAdmin boolean on the subsequent memory write. But now you look at me and say, Adriaan, what are you telling me? This store is protected. This is a protected memory write, right? How could this ever happen? It will immediately crash. And that's the core misconception about store-only bound checkers. So what will actually happen is the bound checker will look up the intended referent that is associated with the pointer you're actually loading from memory, not with the pointer you were supposed to be loading from memory, right? So it will look up the referent of the isAdmin boolean pointer instead of whatever pointer you were supposed to be loading. There is also no pointer you were supposed to be loading because you're not checking the validity of the user ages array read. So there is no concept of what you're supposed to be doing. It's not checked. And so that's the core misconception. That's the core vulnerability in store-only bound checkers. It gets a little bit worse because you could still say, okay, but Adriaan, are attackers really going to figure out where all of the interesting pointers, the isAdmin pointer, are in your program, right? And then they're conveniently located close to the user ages array, right? I don't buy that. You don't have to buy that. Store-only bound checkers explicitly permit information disclosure as part of their threat model. So you can abuse arbitrary memory reads as much as you want. So you can disclose the entire memory contents of the application figure out where all of the interesting pointers are. And then you can do more, you can also craft those pointers. So as part of the payload, in some attacker controllable areas of memory, you can embed pointers together with crafted metadata about them, in this case a crafted fat pointer, and then you can load that one during the memory read. And so here you can really massage the memory, put attacker crafted memory locations close to these exploitable memory reads, and really attack anything you want. And I really mean anything you want. So in a normal bounce checker, at least you won't be able to override return addresses or bounce tables or like any object for which the bounce checker never generates any validity metadata, right? But in some of these bounce checker designs, you're even able to craft metadata to objects like return addresses, bounce tables, so things you really shouldn't be able to corrupt. And if you're able to do that, then you're able to bypass the bounce checker completely. And I want to stress this is not a design or implementation issue with like softbound or with a fat pointer or anything. We analyzed this empirically on softbound. We ran experiments on it. They're also open source. But we also looked at a range of sort of representative other work, also some very recent work. And we looked at whether you can reuse existing pointers in the application, whether you can craft pointers, whether you can target illegitimate objects like return addresses, bounce tables, so really crazy targets. And I guess as is tradition at this point, Intel MPX is the worst of the class, right? So Intel MPX is actually, believe it or not, inspired by softbound. So it's an attempt to provide hardware acceleration for the ID that's presented in softbound and to standardize by Intel. But somehow they messed it up so bad that you can do all sorts of things in this case that you couldn't even do with softbound. A second issue that we looked at is this premise of store-only bounce checkers that you really need invalid writes in order to corrupt security-critical objects in order to perform expressive attacks, right? And the sort of hacker community, exploit development community has known for a long time that you really don't, right? There's snippets like this where you're loading a function pointer from an array. If that array read is exploitable, you can also load any function pointer out of the memory space of the program, and you can, when it's called, you have already achieved arbitrary code execution, right? And so this is also something that has flown under the radar of store-only bounce checker developers who have made some really embarrassing claims about it in hindsight. There's also some more like data-only attack-ish types of attacks you can do, where the type of memory read you can exploit is not limited to pointer reads alone, right? Any data that you read that can be controllable by the attacker can choose what data gets loaded into the admin level variable here, and then that admin level variable can be very security critical, right? It can control whether it spawns a shell. It can also be used to write to another part of memory, in which case you've granted the attacker a write what primitive, not a write what where primitive yet, but maybe subsequent exploitation can achieve that. So both of these are also greatly facilitated because store-only bounce checkers allow you to disclose arbitrary memory and allow you to also craft these things as part of the payload anywhere. So for instance, function pointers of code addresses that you like, you're able to defeat ASLR, disclose interesting code gadgets, and then craft pointers to those gadgets as part of the payload. So it's really not limited to invalid writes alone, what attackers want. There's other ways to bypass store-only bounce checkers. So we looked a little bit at this pattern that we keep talking about, where you load and then you sort of use the attacker-controlled value in an exploitable way, right? We looked at this pattern and we looked at how common this actually is in real-world code. So we looked at the 1,000 most start C and C++ repositories on GitHub. And we defined two data flow patterns that we encoded in CodeQL queries. So one of them is loading a data pointer from memory and then using it in a memory write. Another one is loading a function pointer and then calling it, right? It's kind of, our goal with this is not to say that all of the 1,000 GitHub repositories are vulnerable right now, right? Our goal is to say, imagine if you are an attacker and you have found an exploitable memory read in an application. What are the chances that you can use that read to bypass the store-only hardening, the store-only bounce checker, right? And you can see that the chances are much bigger for the unsafe data pointer read, so for the sort of bypass primitive that we developed, than for the unsafe function pointer primitive, which occurs far less frequently, and which was previously sort of the most expressive way, I guess, to bypass a store-only bounce checker. So you can see that it's actually much worse than we previously thought. I want to stress this point a little bit. If we sort of deconstruct the argument for store-only bounce checking as it has existed in literature for decades, we can see it's in two parts. First of all, invalid writes are necessary for sort of severe or expressive exploitation or for the majority of attacks. And then secondly, store-only bounce checking protects against invalid writes, and so combined store-only bounce checking protects against the majority of expressive attacks, right? And I think at this point we've really debunked both of these, right? We've seen attacks that don't use any invalid writes that are able to bypass store-only bounce checking, or that are able to be very expressive. And then we've seen the sort of core meat of store-only bounce checkers being bypassed as well, right? We can even bypass the store-only bounce check itself. So it's really not much use at this point, I think. But I'm gonna make it a little bit worse anyway. So when we look ahead, so we've looked at the past, right? What have we done with store-only bounce checkers in the past? But when we look ahead, what are the trends in bounce checkers, and what holds the future for store-only bounce checking? And there's this really promising trend that I actually really stand behind, which is a little bit involved to explain. So in many sort of efficient bounce checker designs, we frequently have some bits in the pointer that are part of the bounce checker design, right? So for instance, a bounce table index in a pointer-based bounce checker, or like the more significant bits of the pointer in an object-based bounce checker, doesn't really matter. We want to protect those bits from corruption by the attacker. There's two main ways an attacker can corrupt them, either by overwriting them with a memory corruption, but the bounce checker is there to prevent it, so that's sort of a self-dependent protection, but also a relative pointer override. If you give the attacker access to a 64-bit pointer arithmetic primitive, then the attacker can sort of, by just adding a large offset to the pointer, can corrupt even the most significant bits of the pointer, right? And so this is essentially how that would work, how an attacker can reconstruct a valid pointer into object B from object A. If the attacker is able to leak both pointer B and pointer A, they can compute the offset between them, then add that offset to pointer A, and that's essentially a reassignment of pointer A to pointer B, right? So you've fully reconstructed pointer B. And so you've sort of broken the immunity of the immutability of those in-pointer bits. And so historically, how we've protected against this attack, we've known how to do this for ages, is to do pointer arithmetic, right? So every time to constrain pointer arithmetic, every time you do pointer arithmetic, we sort of mask off all of the bits that are too high and that would corrupt the in-pointer bits, right? So we sort of take care of this approach. But this has some issues. Pointer arithmetic is hard to detect. You will crash some applications that do use relative pointers. Like this has some issues, also a lot of overhead. And so there's this interesting trend in bounce checker design that now uses cryptographic immutability. So low latency crypto that's available in like things like ARM pointer authentication, stuff like that. Now we're able to embed checksums of those in-pointer bits together in the pointer, right? And so if they're ever been modified by some out-of-bounds arithmetic, then we will detect that the checksum fails and we will kill the application. The problem with that is, of course, that now if you really do this sort of involved arithmetic where you do this relative pointer offset attack, you reconstruct pointer B from pointer A using the offset between them, there's no way for the cryptographic immutability to detect that, right? And so the way these bounce checkers, these modern bounce checkers with low overhead protect against that is by making sure that an attacker can never leak authenticated, cryptographically sealed pointers. And so they really depend on the protection on memory reads to prevent this attack, right? Unfortunately, the reason why I'm really stressing this point is that we've already seen a bounce checker that failed to do this. So this PACMEM is a CCS 2022. This is a cryptographically sealed pointers bounce checker that did provide a store-only working mode. And so there you're really combining two of the worst parts of security vulnerabilities in bounce checker together. And so that's why I want to stress that. Don't do this, right? If you're going to do store-only bounce checking, at least don't use this modern type of bounce checking that has low overhead. But after this whole talk, I can see that some of you still want to use store-only protection, right? It's still just too interesting of a proposition that you can instrument the minority of memory accesses and you can protect against the majority of attacks. And so I have really good news for you. we actually found in the paper that data flow integrity, which is a different type of memory protection, is not vulnerable against store-only bypasses. So with data flow integrity, you compute sort of what objects are accessible to a certain memory access at compile time, so with pointer analysis, right? Really expensive computation, has a lot of problems, but at that point, you've sort of identified a set of objects, a set of intended reference for a given memory access, and you can enforce that at runtime, right? And there is no intended reference being passed around in the memory. There is no way for an attacker to influence that with memory reads. So that's an interesting solution. There's also some other stuff that I invite you to read the paper about, some impact on other fields of bounds checking, some support techniques. And so I invite you to read the paper. I invite you to check out the experiments. All of them are open source. And I invite you to ask me questions about this work. Thank you.
Thank you very much.